All right, we're on the guided practice. This is page 246. The first two, the directions say use a diagram to list the factor pairs of each number. I want you to recognize that this does not ask you to use a factor tree or a ladder diagram to find the prime factorization. We're going to do that later in the page. All we're trying to do is find the factor pairs. So what I do is I like to use what I call the rainbow method. I like to list the factors in order from least to greatest. So I do this. 18 would be 18, 1 times 18. And when it says use a diagram, you can just do this. 1 times 18 is 18. And 2 times 9 is 18. And 3 times 6 is 18. That's the diagram. That diagram helps us make sure we got all the factors. We didn't miss any pairs. Put a little comma there in between the numbers. So the factors of 18 are 1, 2, 3, 6, 9, and 18. 52. There are 3 pairs. So it's just like the last one, kind of. 3 pairs, so it's going to be 1 times 52. 52 is an even number, so the second factor is 2. And the second to last factor is half of 52, which is 26. And then the third pair, we're going to just have to kind of guess and check, I guess, or just use our facts. So I just go in order 1, 2, 3. 3 does not go into 52. It goes into 51, but 4 does. 4 goes into 52 13 times. And then I guess you're supposed to list the factors. I guess you can just do it. I don't know. I have them listed here, I guess, but it doesn't matter. Supposed to list them on the line. It would be 1, 2, 3, 6, 9, and 18. And the factors of 52 are 1, 2, 4, 13, 26, and 52. Next, we're on number 3. It reads, Carl needs to build a stage that has an area of 72 square feet. Remember that area is found by multiplying the length times the width. So this is very much a factor problem. Basically, if I give you the area, you have to name 2 factors that would multiply together to give that area. The length of the stage should be longer than the width. What are the possible whole number measurements for the length and the width? It just said that the length is going to be longer than the width. So when I come up with pairs, all the bigger numbers have to be the top number because that's the length. The smaller numbers have to be the bottom. This missing number right here is 1, and I know that because the area of 72 could be found by doing 72 times 1. In other words, if I were doing number 3 the way I did number 1, I would have 72 first. Let's do it right here. The other way you could do this exact problem would be like this. The factors of 72 are 1 and 72. And you would have some kind of a diagram showing that it's 1 times 72. The next one's going to be 2, which we have right here. And 2's partner, well, 2's partner is going to be half of 72. You can find that by dividing 72 by 2. 2 goes into 7 3 times. 3 times 2 is 6. Get a difference of 12. 2 goes into 12 6 times. 6 times 2 is 12. That's the answer. It's 36. All right, so now we just kind of keep going, and we can use our multiplication chart to figure out if 3. Do you notice the width are my small numbers? The next, if I go back to this one right here, I'm trying to get you to recognize that this problem right here is the same thing. Would 3, this is the question, would 3 go into 72? And if you look on your multiplication chart, you'll see that it does. It goes in 24 times. You don't have to know your 3's up to 72, but you have to have a tool that can figure it out. Look on your multiplication chart. Does 4 go into 72? It does, 18 times. Does 5 go into 72? You don't need to look on your multiplication chart because 5 only goes into numbers that end in 5 or 0, and 72 ends in 2, so 5 doesn't go into it. You look on your multiplication chart, does 6 go into 72? It does, 12 times. And does 7 go into 72? Clearly it doesn't, because 7 times 10 is 70. Does 8 go in? Yes, it does. I know my facts. 8 times 9 is 72. And do you see how these two numbers are so close to each other? This would be the middle point where my next number here would be 9, and 9's partner would be 8. And then I can't put that one there because A, it's a repeat, and B, I'm not following those directions where it says that the length has to be longer than the width. So that's how I know I'm done. Not to mention we filled up the table. Cool. All right, that's one way to look at how to find the factor pairs of a number. 72 has a lot of factors. All right, let's move on. We're on numbers 4 and 5 where we're supposed to use a factor tree. and you can use the ones they started for. You should use the ones they started for you. They started number 4 for you. On number 4, we're supposed to use a factor tree to find the prime factorization of 402. And what do you notice about 201? It's exactly half of 402, which makes this a 2. And so this is going to be a prime number, so we circle it. 201 is not a prime number. Now, a lot of kids would be stumped on what this is divisible by. I'm just going to help you. It's not divisible by 2. This is a terrible answer because 2 doesn't go into odd numbers. So the one you have to try next is 3. And here's how you try 3. You just simply go over here and you do 201 on your whiteboard divided by 3, and we're just going to check. Does 3 go into 2? No. It goes into 20 though. 6 times, not 7. 7 times 3 would be 21. 6 times 3 is 18. And 20 minus 18 is 2. Bring down this 1. And 3 goes into 21 7 times. 7 times 3 is 21. The answer is 67. And you may not recognize this, but 67 is actually a prime number. You can look on your multiplication chart, and you won't see any pair of numbers that go into 67. 2 doesn't, 3 doesn't. The only numbers that go into 67 are 1 and 67. So it's even though it's a big number, it's a prime number. So we circle it. So now we go analyze all our prime numbers. We've got a 2, a 3, and a 67. And we could use our multiplication, or use our calculator to check. 2 times 3 times 67 is 402. We got it right. The only thing that'd be tricky is if you weren't sure that 67 is prime, which it is. All right, 36 is not prime, so we put branches. And you could do 2 times 18, or you could do 3 times 12, or you could do 4 times 9. And it doesn't matter which one you choose. I'm going to do 4 times 9. Neither 4 nor 9 are prime. So I'm going to do branches off of my 4, and 4 is made up of 2 times 2, and both 2's are prime. And then my 9's are 3 times 3. 3 times 3 is 9. And how do we write that? Well, we put 2 first, and we don't do 2 times 2 times 2, 3 times 3. We do 2 to the second power because there are 2 2's, and then we multiply that by 3 to the second power because there's 2 3's. So there's 2 times 2 and 3 times 3, and we can check that. 2 times 2 times 3 is 36. If you chose to do a different set of branches, like 2 times 18 or 3 times 12, you would have gotten the same answer. Your path would look different, but you would get the same answer. All right, let's keep going. Let's review the ladder diagram. We've got the ladder diagram for 64 and for 27. I'll do 64 first. 64 goes inside this upside down division sign. And I always like to do 2's. Well, you have to do 2's actually. You can't put an 8 here. You could. Here's the problem with this though. I never thought about this. With a, I'm going to compare 64 on a ladder diagram to 64 in a tree diagram. If you wanted to do this and you wanted to go 8 times 8, you can do that because then you can branch out your 8's. That's okay. You can't do that on a tree on a ladder diagram, because if I put an 8 here, the first rule of doing a ladder diagram is this has to be a prime number, and 8's not a prime number, so I'd actually need to do another ladder here and it would be a disaster. So you can't put an 8 there. You don't have quite the freedom when it comes to ladder diagrams as you do tree diagrams. This has to be a prime number, and the prime factors of 64 include 2. And so how many times does 2 go into 64? Well, half of 64 is 32, so I put a 32 here. And I got to put a prime number here, and I'm going to try 2 again. Does 2 go into 32? Of course it does. 2 goes into all even numbers. 2 goes into 32 16 times. And does 2 go into 16? Of course it does. 2 goes into 16 8 times. And 2 goes into 8 4 times. And 2 goes into 4 twice. And remember, we don't stop till we get a quotient of 1, and we don't have a quotient of 1 yet. So what goes into 2? 2 does. How many times? 1. Now we're done. And the answer is all of these factors on the outside. And they're all 2, so we don't need to write 2 times 2 times 2 a million times. We need to count the 2's. There are 1, 2, 3, 4, 5, 6. That's the exponent. The base is 2. The exponent is 6. I know that seems tricky, but I'm going to prove it now by counting out 6 2's. There's 1, 2, 3, 4, 5, 6. I'm going to count actually before I equals. There's 1, 2, 3, 4, 5, 6. That better be 64. It is. Boom, got it. Let's check out 27. 27 is going to be a little different than the last one because it's not divisible by 2. So we have to know our facts really well. It's actually divisible by 3. That's a prime number. And 3 goes into 27 9 times. And what prime number goes into 9? 3 does. 3 times. And what prime number goes into 3? 3 does. 1 time. That means I'm done. And that my answer is 3 3s. That's not 3 times. I know you might be tempted to do this 3 times 3 times 3. But the better way to write that is to write 3 to the 3rd power. And if you just don't believe that, you can punch it in 3 times 3 times 3. It better be 27. It is. We got it right. Nice work. So the essential checking question at the bottom says, tell how you know when you have found the prime factorization of the numbers. Well, it's got to be when all of the factors are prime. I don't know if we need to write anything else. I guess we should say this. When all the factors are prime and they multiply together to make the original number. So 2 things have to happen. They all have to be prime and the calculations have to be correct. Like it'd be one thing to get all prime numbers, but if you made a computation error, then it would be invalid. So, okay, great job. You're done with page 246.